Good afternoon, everyone. My name is Bobby. I'm from Trinity College Dublin, and together with my colleagues, I'd like to present to you some work today, which is entitled The Modification of the Theory of Critical Distances to Predict the Effect of Multiple Stress-Rising Features on Resulting Fatigue Failure of Selectively Laser-Melted Titanium-64 Material. Before I go into the detail of the work, I'd just first like to outline the problem statement a little bit more to address the question with which we sought to answer by carrying out this study. And that is to assess multiple stress-rising features in SLM Ti64 material via this modified theory of critical distances approach, which includes the design of small voids placed within near proximity to an external stress-rising feature. So if I can draw your attention first of all to the image on the screen here, there are a few key features to the specimen designs which I'm going to show in a few minutes, which I'd like to first of all point out. Amongst all specimen designs, we implemented an external stress concentration. However, in the case of half of them, this was in the form of a macro size notch, which was geometrically induced via the design process. And in the case of other specimens, we implemented a plain fatigue specimen design with a rough SLM surface finish, which we considered as a micro notch, or small stress concentration. Internally then, we also had a second stress concentration implemented within the design of all these specimens. This was kept constant throughout and was implemented in the shape of a void, which went right through the thickness of the specimen. And was, as I said, the size was kept constant throughout. The second feature with which we sought to vary amongst the different specimen designs, as well as the external stress concentration, was that of the proximity of both of these multiple stress-rising features, whereby the distance between both was varied on two different levels, which I'll go through a little bit more in a minute. By carrying out this process, we wanted to address the question of whether a modified or alternative TCD method could accurately predict the fatigue performance of additively manufactured titanium-64 material in the presence of multiple stress-rising features. So a little bit more about the justification or the reason for carrying out this work. As we all know, additive manufacturing allows for customized components of a high geometrical freedom. This means that we can have a wide range of varied and complex shapes. And as a result, there is an increased likelihood that we would have multiple stress concentrations in close proximity to each other in our design process. Additionally, this also may include internal cavities. Now, this can be from a design standpoint of view, where they're intentionally impacted upon our part for some reason or another, as you can see an example here on the left-hand side and also on the top right-hand side, where we have intentionally induced cavities, but also from an unintentional standpoint, whereby we may have process-inherent induced defects in the form of lack of fusion or gas pores. A little bit of background on the original theory of critical distance approach for those who don't know it or who are not so familiar with it. It is a classical linear elastic fracture mechanics-based approach that is used to make fatigue predictions. It has been used across a wide range of engineering fields in the past and continues to be today, including that of predicting the performance of additively manufactured parts. A previous study which we conducted prior to this one involved the fatigue prediction using TCD methods on additively manufactured notched titanium-64 material, which included us considering the scenario of a rough SLM surface finish being modelled as a micro notch for the purpose of making TCD-based predictions on the micro stress concentration level, whereby we considered a rough SLM surface finish as a small stress concentrated feature. So with regards to how this works, if we were to have a component, or in this case a fatigue specimen with a large stress concentrating feature in the form of a notch here, and apply a load in the tensile direction, we can focus on the material in the vicinity of our largest stress concentration, or what we know as hotspots. By analysing this stress in a direction that is perpendicular to the applied load, we will get a stress profile that looks a little bit like this, whereby maximum stress will obviously be located closest to the notch tip, and that will slowly dissipate as we move further into the material. By plotting this stress-distance relationship, we will get a curve that looks like so. Using this curve, along with a couple of critical parameters that are essential to performing TCD analysis and which may be calculated from a limited amount of experimentally generated fatigue data, we can make TCD-based fatigue predictions. Moving on from this original approach, or just to clarify that original approach as you see here on the left-hand side, it requires a piece of stress distance information emanating in from the notch tip, or largest stress concentration in our feature. Now, this is all very well and good. However, For components with multiple stress concentrating features, but furthermore, which may include voids in close proximity to larger stress concentration points, we may end up with a scenario whereby our stress distance data is interrupted, as you can see here. And this is the question with which we sought to answer, or the problem with which we sought to address in this work, whereby we wanted to see if we could get around this issue by modifying the TCD or otherwise. In order to do this, then we obviously had to consider a number of different ranges of approaches and come up with a number of new ways with which to consider the TCD in this scenario. The scope of this presentation is a little bit too short to go through each one of these in detail, but nevertheless, I just wanted to highlight that this process was conducted prior to choosing or selecting the best one which worked best across all specimen design sets. Now I'll just go through briefly the experimental setup with which we implemented, which I talked about a few moments ago. This involved the design of four specimen design sets. In the first two cases, we have a large geometrically induced notch on the external of our part, or at the part periphery, in the form of a large notch, as you can see here, 1 and 2. For specimen sets 3 and 4, we implemented a plain fatigue specimen design. However, it had a rough SLM surface finish, which we considered to be a small stress concentrating feature on the micro scale. While all specimens had an internal void implemented some distance in from the part periphery, specimen sets 1 and 3 had a smaller distance between these two stress concentrating features in the region of 0.1 millimeters, whereby specimen sets 2 and 4 had a larger distance in the region of 0.3 millimeters. These distances are crucial with regards to a critical distance parameter L, which we use in TCD predictions, whereby in the range of 0.1 millimeters, we're trying to conduct analysis at a distance that is less than our critical distance parameter L, and at a range of 0.3 millimeters, we're trying to implement predictions beyond at a distance beyond our critical distance value L. Once we produced all specimens via SLM methods, we could then conduct experimental fatigue experiments in the axial direction with a load ratio of 0.1. Each of these color codes corresponds to one of the fatigue specimen sets in question, and we have also plotted a SN curve which indicates the fatigue strength for this particular material in question, which was generated in a previous study but is nevertheless as relevant to the same material which we have used in this study here. In order to make TCD predictions, we also needed to implement or model our specimens within a finite element analysis program. So to make this process as accurate as possible, we wanted to implement the actual dimensions of our specimens as printed into our model. So pore characterization was carried out in the form of SEM analysis to relate or to infer the exact dimensions of our pore into our model, and the same was conducted for the SLM surface, whereby we carried out 2D surface profilometry and measured the maximum depth of the maximum value depth of the surface, or RV parameter, to influence the size of the micronotch which we implemented in our model. This approach here is one of the many that I presented a few minutes ago, or outlined a few minutes ago, and proved to be most universally acceptable across the 4 fatigue specimen sets with which I've outlined. It involves 2 phases, whereby in phase 1 we seek to assess the stress according to TCD methods, beginning at the notch tip, emanating over towards the second internal stress concentration feature and beyond. We assess our stress at the critical point according to TCD methods, which gives us a sigma 1, and this can be translated back to as a fatigue life of N1 cycles according to the SN curve which I presented a moment ago. For the second phase, we consider a crack to exist between our 2 stress concentrating features, and the material and the remainder of the fatigue life of the specimen is considered to begin at the far side of our second internal our second stress concentrating feature in the shape of a void. By assessing the stress here in our second phase, we get a stress of sigma 2, which gives us a cycle of our fatigue life of N2. Adding N1 and N2 together gives us an accumulated fatigue life with which we can then translate back to our SN curve and make a revised TCD-based fatigue strength prediction. These are the results here, whereby we can see that for each of these specimens which we have implemented, the error margins fall within 20%, which is generally considered to be somewhat acceptable in the field of making fatigue-based predictions. Although it must be said, some are a lot more accurate than others, and the model overall would require a lot more work going forward in order to improve it and analyze this data even further. Away from the TCD predictions, just a few observations with regards to the fracture surface, which we can use going forward. For the case of the large geometrically induced notch, we can see that crack initiation begins on either side of its cross-section, with final fracture occurring in the center, meaning that the imposition of an internal board does not really dictate crack initiation and subsequent growth. However, in the SLM, or the plain specimen with a rough surface finish, or micro stress concentration, we can see that the internal board does initiate cracking on this side only, whereby the crack path grows across its entire cross-section and final fracture occurs on the far side. Once again here we can see that crack initiation does not always occur from the surface and is instead dictated by the dominant stress concentration feature. In this example we can see that the crack initiation here in phase 1 begins at the pore and comes out towards the surface. So in conclusion then, the modified TCD approach which we use for the specimen designs considered shows that a universal TCD approach is possible in this regard, considering the scenarios of multiple stress concentrations in close proximity to each other. And with regards to TCD analysis, they pose a solution to work with an interrupted SD curve of data. Fracture surfaces show that the identification of crack initiation point is crucial to influencing the modelling approach taken, and it doesn't always start from the external surface. The dominant stress concentration feature is the most relevant point. However, it must be said that only a 2D scenario was considered across these 4 specimen designs, and going forward, a 3D situation along with other design combinations should be considered in order to improve and validate the model even further. And that concludes the presentation of my work. Thank you very much for listening, and if there's any questions, they're most welcome.
Thank you for the interesting presentation. Is there any question from the audience? Please.
Thank you for your presentation. Can you just go to the conclusion slide?
Yeah.
So you state that the crack initiation doesn't always start from the external surface.
Yes.
Right. But when you split the two cases and then you sum up,
Yes.
you identify the critical distance
Yes.
starting from the surface.
Yes.
So would it be better to, how do I choose it? From the internal or the external?
You're dead right. So like I guess the point I was trying to make, that going forward based on this analysis that we've seen or evidence from the fracture surface, it would be good to influence this evidence back into our model and analyze the TCD the other way around for this specimen design case, and maybe we'll get or more likely we'll get a more accurate prediction going forward for this type of specimen. So yeah, you're 100% right.
Thank you.
No worries.
Any other question? We can proceed.
Okay. The next presentation is titled Wall Thickness and Decay Effect